All right, so in this video, we're going to continue talking about the derivative and specifically about this idea of differentiability at a point. So we're going to study whether or not a function is differentiable at x equals x naught. In other words, it means if you take a derivative, will you be able to evaluate it and get a value by plugging in x naught? Now, remember, just as a real quick review, the derivative f prime of x was this limit as h goes to 0 of f of x plus h minus f of x over h. I've said it so much it's probably starting to annoy you guys at this time. But now remember, we take this derivative, which used to be our slope predictor, and we would then evaluate it at x equals 2 or whatever, which means that we would replace all of our x's with 2's. And the reason why I'm showing you this the way that I am is because the notation that I'm going to put on the screen here in a second in regards to differentiability can look a little messy. But don't let it fool you, okay? Don't let it intimidate you. So we're going to say f prime at x naught exists. IFF, if and only if, we discussed how that's a two-way street there. F prime from the left at x naught is equal to the limit as h approaches 0 from the left of f of x naught plus h minus f of x naught all over h. And here's the big and this won't surprise you when I tell you why. F prime from the right at x naught equals the limit as h approaches 0 from the right of f of x naught plus h minus f of x naught all over h exists and are equal. Now, again, the notation looks so much worse than it really is. In theory, all that I've done is I've taken this derivative, this limit definition of the derivative, and I've replaced all of my x's with the value that I'm interested in this case, x naught. So you can see the x naught there, there, and there, just like I replaced it with 2 a moment ago, there, and there. I did the same thing down here. Now, the only other change in notation would be this subscript here minus and the subscript plus. And if you remember, we're still talking limits, and this whole idea of a limit existing, it has to be equal from the left and from the right. So we're saying that the left-hand derivative must equal the right-hand derivative. So these derivatives must exist and are equal. And so that's the whole idea of differentiability. Now, here in a couple sections, I can give you some shortcuts in terms of deciding whether or not something is differentiable at a point. But for now, these are good definitions to start with. So now I'm going to go ahead and clear the screen, and we'll look at a specific example, one that we'll see again from time to time. Okay, so in this example, we are going to prove that the absolute value function y equals the absolute value of x is continuous but not differentiable at x equals 0. Now, to get this started, it's worth a review. Remember, the absolute value function is really a piecewise function. So we would say that the absolute value of x is equal to x when x is bigger or equal 0 and negative x when x is less than 0. This definition of the absolute value is not discussed nearly enough in algebra classes. Not that it's incredibly important then, but I think it's interesting to know why the absolute value function is the shape that it is, and it's because it's a piecewise function, essentially two lines put together to create one function. And so that's going to be our definition that we're going to need to start with. Now, there's two parts to this proof. We need to first prove that it's continuous. And so to show continuous at x equals 0, remember the definition of continuity, we need to show that the limit as x approaches 0 of f of x is equal to f of 0. So we'll start with f of 0, and it looks like 0 would be included in this top function because of the or equal to. If I plug a 0 in, I get a 0 out. So f of 0 is 0. Now for the limit as x goes to 0 of f of x. Remember, now this is broken apart into two different parts. The limit as x approaches 0 from the right, and the limit as x approaches 0 from the left. So if we're coming in from the right, we're coming in on values that are bigger than 0. So that would again be this top part of the function. So by plugging that 0 in, we do get a 0. Coming in from the left, now we'd be coming in on numbers less than 0. So we'd be using this function here. As we put a 0 in for x, it too spits out a 0. So since these two are the same, that means this limit is also 0. And because the point and the limit match, therefore f is continuous at x equals 0. Okay, so we've proven that it's continuous. So that's half of our problem. Now to show that it is not differentiable, let me separate this a little bit here. To show that it's not differentiable, we're going to go back to those differentiability formulas from before. So to show not differentiable at x equals 0, we'll go ahead and we'll start here with the idea of the right-hand derivative. So this is going to be f prime with the plus on the bottom at 0 equals the limit as h goes to 0 from the right, 0 plus h, absolute value, minus absolute value 0, all over h. And so again, that's just your difference quotient with 0 plugged in for all of the x's. So when you go ahead now and simplify this down just a little bit, we get the limit as h approaches 0 from the right of the absolute value of h over h. When we know, because we're coming in from the right, this is a graph that we've seen before. Since we're coming in from the right, these are all positive values. This final answer here is going to be a positive 1. Now, in terms of the left-hand derivative, now we've got this limit as h goes to 0 from the left, absolute 0 plus h minus absolute 0 all over h. And as you probably suspected, it's pretty much going to the same spot in terms of what the function is. However, because now we're coming in from the left, we're going to be having negative values. And while the numerator is always positive, if the denominator is negative, this is going to give us our negative 1. And so you can see the right hand and the left hand are not equal. Therefore, f is not differentiable at x equals 0. So there's a nice proof and justification to this whole idea. And again, don't let the notation bother you over here. Really just slow down. And I know I'm moving kind of fast in the video, but you have the opportunity to slow it down, pause it, replay, whatever. But just understand, I'm just plugging in the 0 to that original slope predictor formula we talked about from before. Okay? Now, there's one other thing that I want to mention before breaking this tape and going into the next example. It's a theorem. And it's one that if you can remember this one example, you can remember the theorem. The theorem is 2 parts. The first part says that differentiability at x equals a always implies continuity at x equals a. The second part says continuous at x equals a does not imply differentiable at x equals a. And so again, another reason why I use this example is because everybody should be familiar with it. You know that if you look at the absolute value function, you are continuous at x equals 0 just by looking at it. Now, even if you didn't know the definition, most people would say, yeah, you're continuous there. But we've just shown that it's not differentiable. And so the whole idea of ifs and thens type of statements really come into play here. Differentiability does imply continuous. Continuous at a point, however, does not imply differentiable. And that's what we showed here in this case was part 2. So it's a useful example in a variety of different applications that are to come throughout the course. So hopefully it's one that you can relate to later as well. Now, before I end this video real quick, I do want to mention in your text on page 110, page 110 from the text, they've got some really, really good pictures of what are called corners, cusps, vertical tangent lines, and then a couple of kind of interesting ones on the bottom, one just being a discontinuity, and then one they actually call a wild oscillation. But on page 110, the cusp, the corner, and the vertical tangent line are pictures that I really want you guys to take a few minutes and review before jumping into the homework.